So in the previous segment, we talked about BCNF. We defined BCNF. And so now we have an algorithm also to verify whether a relation is BCNF or not. I also have this example and relation A, B, C, D with these functional dependencies, and we identified that this relation is not BCNF. So then the question is, how do I decompose this relation into sets of better relations? So what the algorithm that we're going to describe essentially takes a relation, a non-BCNF relation, and decompose it into potentially BCNF relations. And if it's not BCNF, we can keep going and decompose it eventually into BCNF relations. Sorry, I forget that I have this here, so let me move this a little bit lower. Okay. So if I have a non-BCNF relation, then I want to decompose it. If I get lucky, in my first decomposition, I might end with two relations that they are BCNF. If not, like for example in this case, let's say that one of them is not BCNF, then I keep going. And my algorithm actually recursively guarantees that I will end with BCNF relations. Okay. We will see in a few minutes that every relation is guaranteed to have a BCNF decomposition. But not every relation has a good BCNF decomposition. Remember, a good BCNF decomposition is such that the decomposed relations, when I join them together, they give me the original relation. And the functional dependencies of the decomposed relations are FD preserving. So unfortunately, I might lose FD preservation. But we'll discuss that in a second. So this is my relation. So this relation is not BCNF. And I want to decompose it. So let's go through the algorithm. I will not list it here, but I will go through it so it becomes clear what the algorithm is. I like to do this. I like to write my relation. And I like to do this. And the decomposition starts by selecting one of the FDs that breaks BCNF. Remember, if this relation is not BCNF, then at least one of these functional dependencies does not satisfy BCNF, the BCNF requirement. What is that? That either the functional dependency is trivial, like in this case, or the left-hand side is a superkey. For this relation, we identified that these two break BCNF. And that is why the relation is not BCNF. So let's choose one of them. Let's choose C implies B. So the first thing that I do is I move C here and I compute its closure. What is the closure of C in this functional dependencies? Well, the closure of C is equal to C, B, and B. Remember, these are set of attributes, so the order doesn't matter. So that means that this is going to be my relation. The order doesn't matter, but let's put them in order. This is my first relation. Okay. So let me move this out of here because I don't need it anymore. So this is my first relation. Okay. So that's one side. What is the other side? Well, the other side is it will also have C plus everything else in R not in the other relation. So what attributes of R are not in the left-hand side? Well, let's look at it. A is not on that, so we will have to add A. And that's basically all. Let's assume that we have an attribute F also. Then we will have to add F. Okay. Essentially, the idea is that C is part of both. So the left-hand side is part of both relations. That is what I'm going to be able to use to join them together. Okay. We'll talk about join later. So C needs to be common. This is the attribute that will allow us to put them back together when the time comes. But I need to make sure that the union of the both relations gives me the original attributes. So then I need to put everything else that I don't have on the left-hand side. Okay. So that is my relation. So I don't need this anymore. So let me actually delete it. And this is my decomposition. So C of A. Let's put it in order. So just for the sake of cleanliness. Remember, these are sets, so it doesn't really matter. If you give me CA, that's fine too. Okay. So now I have these two relations. But now the problem is, what are the functional dependencies that apply to each one of these sub-relations? And this is where we use the concept of the projection of the functional dependencies. So what is the projection that I'm looking for here? I want to compute the projection of the functional dependencies on the relation CB of R. And this one will be the projection of AC of R. We already have an algorithm to do that. I will not go through every single step again because it's a little bit time consuming. And but I have done it already in advance. It's here. Let me move this down because I keep. Oh, let me remove myself instead. Okay. So the left-hand side is the projection. The projection of the FDs of R on the projection BCD of R. And the right-hand side is the projection for AC of R. Okay. This is the set, and this is the set. So the projection of BC of D, the functional dependencies that apply to this relation will be BC implies D, CD implies B, and C implies BD. Okay. Notice that this, I can write it in canonical form also. And both will be okay. In fact, I can have the union of these two sets and they will be exactly equivalent. They are all bases of each other. So you can write like this, you can write like that. So it doesn't really matter, okay, at this point. And the right-hand side is interesting because once I compute the projection of the set of functional dependencies, I end with an empty set. So this is set of FDs is empty. Okay. Notice that doesn't mean that there's really not any there's not a functional dependency. It means that we can still have trivial functional dependencies. AC implies AC, C implies C, but they don't really give us any knowledge. What is the primary key of this relation? AC. What will be the primary key of the left-hand side? We actually have two. We can have C is the primary key, because with C we get B and D. With B alone we don't get any, and with D alone, with B alone we don't get anything except B. With D alone we only get D. So the primary key of this relation is B. We'll talk about how to compute primary keys and candidate keys a little bit later, okay? But for this, at this point, we don't care. All we need is just these two sets. So let's go back to the previous page. So now we know that the set of FDs of this relation is, so the FDs are BC implies D, CD implies B, and C implies BD. As I said before, we don't care whether they are minimal bases. We just care that we have a set. And the FDs is equal to empty set. Okay, so now we have the first level of decomposition. Are these relations BCNF? If they're not BCNF, we need to keep going. So we need to verify whether BCNF, and we can do that now because we have all the information that we need. So now, given this information, is this relation BCNF? Well, let's look at that. So is BC a primary key of the, is BC a super key of BCD? Yeah, because if you give me BC, I can compute BCD. The closure of BC is BCD. So this is a super key. Is CD a super key? Yeah, because if I give you CD, you can compute CDB. So this is also a super key. How about C? Is C a super key? Well, if you compute the closure of C, that gives you C, B, and D. So this is also. So this relation is BCNF. So we got lucky. In just one iteration on the left-hand side, we have a relation that is BCNF. How about the right-hand side? Is it BCNF? Doesn't have functional dependencies. So if it doesn't have a functional dependency that breaks BCNF, then it's BCNF. Okay. So a relation with no functional dependencies is BCNF. So this is also BCNF. An interesting aspect is that you can prove, and I want you to think about this, that any relation with two attributes is always BCNF. Okay. It's the proof is trivial. And so in this case, for this particular relation, the one that we identified as not being BCNF, are A, B, C, D, with these functional dependencies that we have on the left-hand side, has a BCNF decomposition that is BCD and AC with this corresponding functional dependencies. So the next question is this decomposition functional dependency preserving? Okay. Given the functional dependencies BC implies D, CD implies B, C implies BD, can I create all the functional dependencies of the original relation and vice versa? Okay. And I will leave it as an exercise to you. Is this functional dependency preserving? We'll talk about it in class, and but I think that it's worth that you answer that question on your own. Okay. Let's leave it at that, and we'll continue in the next one.